All right, so let's get started with this one.
In Florida, there's a special lab studying lightning. ABC's Bill Blakemore went to pay a visit.
At any one moment, there are about 2,000 electrical storms on our planet. It's a constantly crackling ball of lightning, about 100 volts a second. Striking people, houses, power lines, airplanes.
Normal commercial plane about twice a year.
A given plane.
Yeah.
Electrical engineer Martin Newman is in league with Jove himself.
All right, so speaking of lightning,
Is 100.
a couple of things. Number one, the airplane getting struck by lightning. You're on the inside, you're perfectly fine. So the question is why? Okay, so we'll answer that question today. What else? Speaking of lightning, people getting struck by lightning. Most people struck by lightning, do they live or do they die? Common sense will say you cannot survive something like that. The reality is most people do survive. Question is, what makes it survivable? What does it take to kill someone with lightning?
In Glenview, high winds took down a power line.
Once again, you got the power line going up, touching the metal casing of the car. That's the live wire, so which means that the car is part of the circuit. That means that this car is electrified. If you go near this car, forget about touching the car. If you start walking towards it, potentially it could kill you. If you were to touch this car from outside, it will fry you. This is 10,000 volts. But she's perfectly safe as long as she's on the inside. All right, so the question was, why is it that she's safe as long as she's on the inside? And most of you guys say, oh, well, because she's not touching the metal. Guess what, guys? She can touch the metal on the inside, she's going to be fine. So why is it that you're still going to be fine if you're touching the metal on the inside? All right, so that's the question that we're going to answer this week. Also, you can touch the metal on the outside. How's that possible? Well, that's the question that we'll answer next week. So it's 1 week at a time.
Please help me out. Yes, we'll carry you. Hold on. I got struck by lightning.
In August 2003, Matt Thompson was hit by lightning in the hills outside Keystone, Colorado.
A bolt of lightning taken straight in the chest.
It just came out of nowhere.
The direct hit traveled all the way through Matt's body.
I had no clue what happened.
Matt's story was big news. On websites worldwide, the issue was raging.
You almost died.
Was Matt's metal tongue stud the reason he was struck?
So my tongue ring. I don't know, dude. You might have swallowed it. Let me see. Where's your tongue? Let's see it. Oh, it's broken off in there, it looks like.
Body jewelry attracting lightning strikes?
So does metal on your body attract lightning? Does metal attract lightning at all? Okay, guys, notice that most of you guys will say yes to that question. Most of you guys will claim that the metal attracts lightning. That's not a bad claim, given the fact that the lightning rods are are they made up of metal, plastic, wood? You know the answer, right? They're made up of metal. What's the purpose of a lightning rod? The purpose of a lightning rod is to attract lightning to itself. They're made up of metal because metals are supposed to be more attractive to lightning. Or are they? Some of you guys will say, no, the metal on your body is not going to attract lightning because it's too small. Does the size of the metal matter in terms of attracting lightning? All right, so we'll find out. So these are the questions we will get to investigate. Let's talk about Gauss. All right, guys, this guy is going to simplify life for us. He's going to simplify life for us in a sense that the sort of mathematics that we were struggling last time, we're not going to be struggling with that sort of math anymore. Okay, so towards the end of the lecture, we end up doing quite a bit of math. So this guy is going to come up with a way to actually simplify the mathematics for us. Okay, so Carl Gauss, obviously this guy's a mathematician. Look at the year he passed away, it's 1855. 150 years ago, give and take. He was one of Einstein's idols. He's considered to be one of the best mathematicians who ever lived. The guy's German. And recognition, obviously German currency's got his picture on their currency in recognition of his achievements. Einstein ended up using the Gauss's mathematics in developing his theory of relativity, general relativity. That's the theory of gravity. Einstein spent like 10 years working on this theory. Out of this theory, we got the predictions of black holes, possibly a wormhole that might make time travel possible, blah, blah, blah. So that's actually fairly interesting. All right, so Gauss came up with a mathematical method, otherwise known as the Gauss's Law. It's the one that we will discuss today. It's a nice little simplification of this mathematics that we were discussing. Okay, guys, just a hint. The first 5 minutes of the lecture, whenever we jump into the theory, it's abstract. Okay, so you will find yourself a little bit confused. Just let it go. If you don't grasp it immediately, not a big deal. Your mind is going to catch on at some point. So pay attention, and then eventually you will go, oh, now it makes sense. All right, so Gauss's law is based on the concept of flux. Flux, when translated in English, it means flow. All right, so what's flowing in this case is this electric field. Notice that E represents the electric field. So the flux represents how much of this electric field is going to be flowing through this cross-sectional area. That's what's called flux. Flux is flow. What's flowing is the electric field through some kind of cross-sectional area. All right, so that's what we're going to be discussing. All right, so this is known as the Gauss Law. It simply deals with, here's the area. So this is a cross-sectional area. So how much of the electric field, which is going to be intercepted by this area? All right, area is a vector. So notice it's got a size, it's got a direction. All right, so area is a vector, it's got a size, it's a direction, it's got a direction. So which means that it's a vector in essence. So how much of the electric field, which is going to be intercepted by this area, is known as flux. Okay, that's it. Flux means flow. In this case, what it's talking about is the amount of electric field which is going to be intercepted by this area. This represents the amount of electric field which is going to be flowing through this cross-sectional area. Area is a vector, electric field is a vector. All right, so this is known as a dot product. If you haven't seen it already, you will see it when you guys are taking Calc 3. It's a concept from Calc 3. What it means in essence is you're going to be interested in the product of the electric field and the area vector times the cosine of the angle in between. Okay, so that's what the formula says. Well, what's the physical meaning of it? The physical meaning of it is you're going to be interested in the projection of the electric field along the direction of the area vector. So the projection of the electric field times the magnitude of the area vector that you're going to be interested in. So you're looking at the product of the projection of the electric field and the area vector. That's what it means. So which means how much of the electric field is going to be along the direction of the area vector. Right, so the cosine of the angle of the electric field is going to be the projection or the component of the electric field along the direction of the area vector. Okay, so you're looking at the product. So we simply put, this means how much of the electric field is being flowing through this area. So this mathematical expression tells you the flux, the amount of electric field flowing through this area. As it so happens, all right, so formula is going to have one more step to it. This Q is going to represent the charge, which is going to be responsible for the electric field. All right, so the flux is going to depend on the net charge within the Gaussian enclosure. Okay, so the next question is, what the hell? What are we talking about, the Gaussian enclosure? Okay, so that's the next part of the story. The only thing you need to know, we'll just write this down. The only thing you need to know is flux represents flow. What's flowing is the electric field through some kind of an area of the Gaussian enclosure that is the complete statement. So that's the total electric field intercepted by an area is known as flux. All right, it's a simple mathematical definition. We'll add on to it. Okay, so the flux is going to be caused by the source of the electric field. Source of the electric field is going to be the charge, just for now. Okay, so we will have to kind of peel this off a little bit more because there's more to the story. All right, so flux means flow. So we will get to use the Greek letter phi for it. So it's going to be F. E is the electric field, A is the area of the enclosure, whatever that means. Just it's the cross-sectional area in this case. All right, so this epsilon naught is our constant. I gave you a warning before I said keep track of this. This thing is going to keep coming up. Eventually, it's going to put a speed limit to how fast the electric field can travel. All right, so let's build up our intuition a little bit more. Coming up with examples. So let's talk about flux. There are 3 kinds of fluxes that we'll discuss. Flux generated by a positive charge. All right, so the positive charge is the source of the electric field. And then what we will do is we will draw a Gaussian region around it. So the Gaussian region is an imaginary region. It's a 3-dimensional region usually, which is going to have an imaginary surface area. So you got this Gaussian surface of the Gaussian region. All right, so this is going to be your Gaussian enclosure. Okay, so the flux is going to be caused, the flow is going to be caused by the net charge on the inside the Gaussian surface, inside the Gaussian enclosure, inside the Gaussian region. Okay, so it's the same thing. So the net charge on the inside of the Gaussian region is going to be responsible for flux in essence. Okay, so in this case, the flux is going to be positive. Positive flux means outflux, which means that the electric field is outflowing in this case, it's flowing out. So the positive flux is going to be outflow, outflux. All right, so we can have a negative charge. We can have a region that contains positive and negative charges. And we can have a region that contains no charges. All right, let's focus on a region that contains only a negative charge. All right, so here's our region that contains a negative charge. Okay, so we just want to figure out the flux of this region. So the next thing you need to do is you need to turn this into a Gaussian enclosure. So you will have some kind of a Gaussian region. Once again, guys, this is a 3-dimensional region. So you're looking at a 3-dimensional Gaussian region that's going to be a spherical Gaussian region, which is going to have a Gaussian surface. So the flux is going to be, it's going to be generated by the net charge within the Gaussian region. In this case, it's going to be a negative charge, which means that we end up getting a negative flux in this region. All right, so negative flux means influx. Opposite flux means outflux. Okay, so this is an influx, which means that the electric field lines are pointing into the Gaussian region from outside, obviously. So electric field lines are being intercepted from out in, from an outward direction to the inward direction. All right, so here's our third region. The third region is going to contain two charges, equal positive and negative net charge. So what is the net flux within this region? So what we'll have to do is we have to come up with a Gaussian region. Once again, it's an imaginary region. It's going to encompass our charges. All right, so what do we have? So the flux is going to be caused by net charge on the inside. So what's the net charge on the inside? You have a positive charge and you have a negative charge, so they will add up to 0, right? So in this case, the flux is going to be 0. Speaking of flux, net charge on the inside is what causes flux. Okay, that's one way of looking at it. Also, flux is the strength of the electric field intercepted by area of the Gaussian region, right? Now, take a look at the number of electric field lines leaving the region and take a look at the number of electric field lines entering the region. All right, so number of lines leaving, exiting, and entering are the same. So which means that the net flux is going to be 0. So that's the second way of looking at this. It's visual. All right, so we get a negative charge here. That's fine. But we're interested in the net flux of this region. So what's the net flux of this region? That net flux of this region is going to depend on the net charge on the inside. There's no net charge on the inside. Net charge on the inside is going to be 0. Okay, all of a sudden we got the overall interpretation of what's going on. So flux means flow. What's flowing is the electric field. And that flux represents the amount of electric field intercepted by the area of a Gaussian region. Right? The area of a Gaussian surface is the amount of electric field which is going to be intercepted by a Gaussian surface. That's what it means. Which depends on the net charge on the inside. If the net charge is positive, you end up getting a positive flux. So that's your outflow. If the net charge is negative, you end up getting an inflow, negative flow. If the net charge is 0, no flux. Okay, in this case, you have charges on the inside, but the net charge is 0. And this region contains no net charge, so it's going to be 0 once again. All right, so we kind of got the overall definition of it. I think we got a nice intuitive sense of what's going on. All right, so that intuition that we're building up is going to help us. Okay, so this is a region, overall region that we're looking at. All right, so the region contains only 2 charges. All right, so let's talk about the Gaussian region. Gaussian region is an imaginary area. Okay, an imaginary area that helps you to calculate flux. And in essence, it's going to help you to figure out the electric field within that region. Okay, you get to decide where you want to draw your region. It depends on the problem. Okay. Okay, so let's pretend that I want to know the flux within this region. So this little thing that you're looking at becomes our Gaussian region. This is S1 represents the surface area of the Gaussian region. The charge inside is going to be positive. So what does it mean? That means that you end up getting a positive flux, flux within this region. If you're interested in the flux here, so you draw your Gaussian region here. So here's the S2 is the surface area of the Gaussian region here. That charge within the Gaussian region is negative, so that gives you an influx. All right, so which means that the electric field lines are pointing into the region from outside. All right, so this gives you a negative flux. All of a sudden, if you're interested in the net flux within this region, so S3 represents the Gaussian surface of the third one, that charge inside is going to be 0. So what does it mean? The net flux, the flux within this region is going to be 0. If you're interested in the flux of the entire region that you're looking at, that becomes your S4. So this becomes your fourth Gaussian region. So now flux is caused by the net charge on the inside of the region. So if you got a positive charge, you got a negative charge. So which means that the net charge is going to be 0. So the net flux is going to be 0 in this case. All right, so problem number 1. Okay, so we're trying to figure out the flux within this region of the, we're looking at the overall flux of the cylindrical region that we're looking at. So this cylindrical region represents our Gaussian region. All right, so notice that it's a symmetrical region, got the shape of a cylinder. So what is the net flux of the electric field through the surface that we're looking at? All right, guys, this should be fairly easy to figure out. I'm guessing that the net flux of this region is going to be 0 because the net charge on the inside is going to be 0, but that's not the way we'll do it. Okay, because you guys are taking engineering physics, we have to be a little bit more mathematically rigorous, evidently. All right, so remember the area is a vector. Okay, so it's an area is a vector, and the electric field is a vector. Okay, so whenever you're looking at the dot product, electric field is to the left. Okay, so how much of this electric field is going to be going through the area of the cylinder on the side? Okay, so area of the cylinder on the side is 90 degrees to the electric field. So 90 degree cosine of 90 degrees is going to be 0. So which means that none of this electric field is going to be leaving this region sideways. So the flux from that direction is going to be 0. All right, here the electric field is pointing in inward direction. The area vector is pointing in the opposite direction. So what do we have? Angle is going to be 180 degrees. So cosine of 180 degrees is going to be -1. So the contribution of the electric field to the flux is going to be negative times E times dA. Here's the electric field is in the same direction as the area vector, so the angle is going to be 0. So the cosine of 0 is going to be 1. So this is E times dA is going to be positive here. E times dA is going to be negative here. So they will add up to 0 in essence. Okay, so let's do it again. This is going to be fun. All right, so we will have to kind of use the formula for this one, despite the fact that conceptually I know it's going to be 0 because the net charge on the inside is going to be 0. Okay, but at the same time, I want to make sure that our mathematical expression makes sense. All right, so the electric field outside is from left to right. Here the electric field vector and then the area vector are in the same direction. So the angle is going to be cosine of the angle 0 is going to be 1. Here the electric field and the area vector start pointing in opposite directions. So the cosine of the angle 180 degrees is going to be -1. All right, so whatever the contribution you get from here is going to be positive. Whatever the contribution you get from here is going to be negative. So you end up getting the same values. This value minus that value is going to add up to 0 in essence. Okay, so it was straightforward. Okay, here's a second problem, which is straightforward, except there are a bunch of numbers here. I'm not going to worry about the numbers. This is just too easy of a setup to waste my time using numbers. Okay, so the thing to focus on is we got two Gaussian regions. Here's the surface area of the first Gaussian region. Here's the surface area of the second Gaussian region. Okay, so the flux of the first Gaussian region is going to be positive, negative, or 0. Okay, immediately you know it's going to be positive because it contains a positive net charge on the inside. All right, so this is a positive net charge. All right, so it's going to give you an outflow of positive flux. Now, if you're looking at the second region is going to contain one positive charge and two negative charges. And I'm looking at the values. Positive charge is going to be 3 something. Negative charge, this is okay. This is 3. This is -5. This is almost -3. So negative charges add up to a much larger negative value than a positive one. So net flux is going to be negative in this case. So it's going to be pointing in the inward direction. Doing it numerically doesn't really do anything. So I don't want to waste time on it. Okay, want to do something interesting, the Coulomb's law. Let's come up with the Coulomb's law using the Gauss law. Okay, so I just want to give you a few demonstrations of it, and this is one of them. All right, so positive charge at the center. This becomes our Gaussian region. Okay, Gaussian regions, usually Gauss' law works really well with the symmetric distribution patterns. Okay, so point charge, assuming that it's spherical, you can just encompass it within a spherical Gaussian surface. Okay, so it's gonna work out. I don't care what kind of geometry you use, it should still work out. All right, so let's use that setup. So the example is gonna be a point charge. And then what we'll try to do is we're gonna try to come up with the Coulomb's law. I think that's what we wanna do. All right, so positive charge is the emitter, transmitter. So it's gonna generate the electric field lines. So what I'm gonna do is I'm gonna place my Gaussian region around this. So this becomes our Gaussian surface. So flux represents the amount of electric field flowing out of this region, area of this region. Oh, I wanted to use the calculus, but okay, so let's use basic algebra. It's the same, more or less. All right, boom. All right, so isolate E, divide both sides by the area, and that's it. We end up getting a nice little expression. All right, so this is the area of a sphere. All right, so the area of a sphere, in this case, is going to be 4 pi r squared, so I just plug it back in. All right, so let's clean this up. We got 4 pi epsilon naught, that's going to be our constant. Q divided by r squared is going to give us the strength of the electric field for a point charge. All right, so this expression that you guys are looking at, 1 divided by 4 pi epsilon naught, is going to give us the strength of the electrostatic force. Okay, that's it. So we end up getting the strength of the electric field due to a point charge. All right, so this was an easy derivation. Okay, let's just go through this using algebra. Okay, when I do a review of this lecture next time, I'm just going to switch to the calculus value. Okay, remember I kept saying that the Earth is negatively charged. Initially, the Earth is negatively charged. So how do we know that? How do we know that the Earth is initially negatively charged? Okay, so where do we get that idea from? Okay, so the reason why we know that the Earth is negatively charged. Okay, so this is going to become number 7. Is because of the following. You can measure the strength of the electric field, and the strength of the electric field, whatever the electric field is, it's a vector. It points in the downward direction. It points towards the Earth. Because it points towards the Earth, that's how we know that the Earth is negatively charged. Okay, remember guys, the electric field points away from positive charge and points towards a negative charge. So which means that the Earth has a negative net charge. Okay, so what I'm going to do is I'm going to place my Gaussian. Okay, I have to redo this problem. Okay, I would have to place my Gaussian in reality outside of the net charge, not inside. This problem needs to be reworked. I must have been distracted by something as I was doing it. Usually I do this late at night, but no excuse, this is not late at night. All right, so we got the electric field pointing towards the Earth. That implies that the Earth is negatively charged. So what is that net negative charge? Okay, so we know the radius of the Earth. Okay, the thing to do is we have to place the Gaussian exactly right at the surface of the Earth, but we need to place it exactly just slightly above where the net charge is. Okay, so this thing green has to be outside, and the net charge should be contained within it. Okay, so that's the reason why I have to redo this. Okay, so we kind of got everything that we need. So we know the strength of the electric field. We know it's pointing in the downward direction. So what is the net charge? So that's what we're trying to figure out. Here's the radius of the Earth in terms of meters. Should have to look that up. All right, so here's the generic formula for flux. And obviously, the portion of the formula that matters is strength of the electric field times the area. Depends on the net charge on the inside. Okay, guys, these are vectors. All right, so area vector and the electric field vectors are pointing in opposite directions. All right, so which means that the cosine of the angle is going to be 180, so which means that this expression is going to be negative. All right, so I place a negative sign here. Okay. All right, so solve for Q. And then when you solve for Q, obviously we end up getting numbers, but there's going to be negative up front. All right, so you plug the numbers in. Area in this case is going to be the area of a sphere. So it's going to be 4 pi r squared, due by substitution. And then plug the numbers in. And I don't know if I did that. I did that. All right, so it gives you a negative number. Okay, so just as we expected. This is how we know that the Earth is negatively charged. Okay, how do we know that? Because you can measure the value of the electric field and it's pointing in the downward direction. That's it. All right, so the electric field downward direction, which means that the Earth is not neutral. That means that it's negatively charged. So it's got a slight negative charge. Okay, now let's see. Okay, so this one is going to be a derivation. Okay, so what if you have a charge distribution in a line? All right, so charges are distributed along this direction. So it's a line charge distribution, linear charge distribution. All right, that's what I meant to say. So the charges are distributed linearly. So you got a net charge here, you got a net charge here. So everything is in the downward direction. So how do you figure out the electric field due to linear charge distribution? It's a derivation. Derivation is a process of solving a problem. All right, so a couple of things that we will have to discuss. Okay, so volume charge density. You get a charge and then you distribute the charge throughout the volume uniformly, so it's going to give you your volume charge density. If you take a charge and distribute it over a surface area, that becomes a surface charge density. If you got a charge, if you distribute it along a line, it's known as a linear charge density. All right, so net charge gets distributed onto a volume, onto a surface area. It gets distributed along the length of a line. All right, so we got different charge densities. All right, so cylindrical symmetry. All right, so you got a line charge density. The charges are uniformly distributed, linearly distributed in this direction. So what you need to do is you have to draw your Gaussian. So your Gaussian region needs to encompass all the charges that you're looking at. So the best shape that fits this is going to be a cylindrical shape that you're looking at. So that's going to be our Gaussian surface. Within the Gaussian surface, you have the net charge in essence. All right, so this is the length or the height of the cylinder. It's got the radius. Okay, so the circumference is going to be 2 pi r. That's it. So we're going to be interested in the electric field intercepted by the area of the cylinder, which is this area of the side of the cylinder that you're looking at. So here's the net electric field, which is being intercepted by the area of this cylindrical region that you're looking at. Okay, so okay, so this is the notation which is missing from the earlier problems. Okay, so all right, so this is the notation that we will get to use using calculus. Okay, so this is the Gauss Law. So this is the electric field vector intercepted by the area vector in the differential form, so, which means that the flux is going to depend on the net charge on the inside. All right, so E is a vector, dA is a vector. Obviously, cosine of the angle matters. Notice that the direction of E and A will be the same. It's a symmetric distribution pattern. So electric field vectors and the area vectors will always be parallel to each other. So which means that the angle is going to be 0. Cosine of the angle of theta is going to be 0. So cosine of 0 is going to be 1. So as a result, I can take this expression and I can rewrite it as such. All right, so the electric field strength is going to be constant, so I'm just going to pull that out. All right, so you see that there's a wiggle. You've got some kind of circle here. The circle is going to represent the direction of integration, something that we will discuss next time. Okay, let me just make up that portion of the lecture. Okay, so in essence, this is going to give us the area of the geometry that we're looking at. So this is the differential of area. In this case, our area is going to be a cylinder, so it's going to be 2 pi r. Circumference times the length, the height is going to give us the area. So do a back substitution. And then isolate E. Oh, wait a minute, we have to express Q, the net charge on the inside, in terms of the linear charge density. So Q could be expressed in terms of linear charge density times the length. So do a back substitution. Notice that the length is going to cancel. It's going to cancel out from both sides. And now isolate E. That's it. All right, so this gives you the strength of the electric field due to linear charge distribution. All right, so this is a linear charge distribution. So notice that you have a linear charge distribution and you're interested in the strength of the electric field because of it, due to it. And Gauss's law is a really great way of actually analyzing these linear charge distributions. It's an amazing way to figure out the electric field due to a linear charge distribution. All right, so that's how they are used. We'll do more problems next time. More likely we'll repeat some of them.
As Apollo disappeared beyond the clouds, Commander Pete Conrad reported catastrophic failures to the electrical systems. Conrad was right. These photographs revealed that it was struck, not once, but twice, by lightning that came seemingly from nowhere. Quick thinking by Mission Control helped them restore power, but it was a close call.
We've had a couple of cardiac arrests down here too, Pete. I think we need to do a little more all-weather testing. Amen.
It was a problem that needed urgent attention. NASA dispatched test pilots to seek out thunderstorms. Their missions took them through turbulence and hailstones, which could tear a jumbo jet apart.
It's one of the very early strikes that we had, where it struck the nose boom, as many of our lightning strikes did, and it then swept up over the top of the windshield, down that metal bar that was over the top of our heads in the canopy. And I could just happen to look up, and I could see helical chunks of plasma as the lightning channel broke apart as it flew back over the top of my head.
The onboard camera revealed something totally unexpected. The plane wasn't just intercepting lightning, it was actually triggering it by interfering with the electrical field inside the cloud. As Apollo 12 flew through the cloud of charged ice particles, it left a wake of hot ionized gases and conductive contaminants. The exhaust became a huge streamer, and the burning rocket plasma a giant lightning rod.
All right, so the question is, now we're about to have the answer. So airplane is getting struck by lightning. You're on the inside and you're perfectly safe. How does the miracle happen? Okay, guys, number one, no miracle happens. This got nothing to do with miracle, just good science. Okay, so you'll be 100% safe as long as you're on the inside. Why? But the reason is because lightning usually deposits same charges onto a metal surface. Okay, so here's my airplane. Looks like a sphere, shape doesn't matter. All right, so the lightning is going to strike. So the lightning is initiated, and then all of a sudden this light charges, net charge is going to get deposited. In this case, negative charges are being deposited onto the metal surface. Metal is a conductor. All right, so the metal has no net charge. As soon as you place a net charge onto a metal surface, individual charges, because they are like charges, they will repel each other. The furthest that they could be repelled to will be the surface. All right, so all the charges get repelled to the surface and they will remain at the surface. They're going to try to get as far away from each other as possible. The furthest that they can get from each other will be the surface. That's it. So like charges can never penetrate in through the surface. Absolutely. They will never be able to penetrate into a metallic enclosure. Because the like charge will get repelled to the surface immediately. So all of a sudden the surface is going to become charged. The net charge is going to remain on the surface. So if you deposit negative charges, the net surface is going to be negatively charged. That's it. So net charge is going to be negative. No net charge is going to be found on the inside. And so because metal is neutral to begin with, the like charges can only repel each other, so they will be repelled to the surface. So the surface is going to become charged, not the inside. All right, so what does it mean from our perspective? What that means is as soon as there's lightning, as soon as the lightning strikes a metallic enclosure, like an airplane or a car or a Faraday's cage, they all mean the same thing. Net charge remains on the outside. All of a sudden, I'm going to place my Gaussian right within this region, right under the net charge. So if that's the case, here's my Gaussian. Okay, so let's check to see what's the strength of the electric field on the inside is going to be. All right, so you solve for E, so this is the expression that you come up with. So E depends on the net charge on the inside. So what's the net charge on the inside? There's no net charge on the inside, guys. The net charge is on the outside. Net charge on the inside is 0. If the net charge on the inside is 0, electric field on the inside is going to be 0. So what does it mean? Electric field is what causes force. Electric field acting on the charge is going to induce a force on it, which means that it's going to force those charges to go through your body. If there's no electric field on the inside, there's no force, electrostatic force acting on these charges, forcing these charges to go through your body. Which means that there's 0 chance for you to get shot as long as you're on the inside. All right, so there's nothing forcing the charges to go through your body. There's no electric field. So there's going to be 0 force acting on the charges inside that region, which means that there's absolutely no chance of you getting shot or electrocuted by what's going on outside of the metallic frame or the enclosure. You can touch the metal on the inside with 1 hand, 2 hands, and then 3 hands if you got 3. You can lick the metal if you want to. It makes no difference. You're 100% safe as long as you remain within that metallic enclosure. All right, so the mystery. So the lightning is, whenever it strikes, it's outside of a metallic enclosure. Net charge, positive or negative. Electric surface becomes charged. There's no net charge on the inside. As a result, the electric field on the inside is going to be 0. If there's no electric field, there's no reason for you to get shot. All right, so it's the exact same concept. So let me repeat. Electric field inside a hollow conductor or conductors, whatever. The shape doesn't matter. It could be a car. It could be an EFO, metal. It could be an airplane. So here's your hollow conductor. And the lightning strikes, it's going to deposit electric charges. Okay, so because metal is a conductor, the net charge is going to be repelled to the surface. So net charge is going to reside outside. So what you do is you draw out your Gaussian region right at the surface where the surface is, under the net charge, underneath the net charge. So within the Gaussian region, the net charge is going to be 0, obviously. So what's the strength of the electric field on the inside? If there's any sort of electric field on the inside, which means you will get shot. If there's no electric field, you'll be fine. So we use the Gauss Law. Electric field due to the net charge on the inside. Solve for E. This represents the net charge on the inside. No net charge on the inside. No electric field on the inside. You're 100% safe. That's it. All right, so the extra charge is always going to reside outside of a metallic enclosure. All right, and none of the excess charge will be found within the body of a conductor, so which means that there's not going to be a net charge on the inside. All right, case in point, this picture was taken probably 70, 80 years ago. Notice that the tires don't help. All right, so lightning, minute lightning is going to hit with the tire.
If you can't do that, you should get into a metal car.
The car's metal body discharges the current away from the driver and the wheel.
If you can't do that, you should get into a
metallic enclosure is like a car. It's just about the safest place for you to be during a lightning storm. All right, so the electric charge will be repelled to the surface. You're on the inside, you're going to be 100% fine. You can touch all the metal you want. Makes no difference. All right, so pick out the best answer, put it in the chat. All right, so the best answer is D, right? So inside a metallic enclosure, you yourself is the safest place to be.
True or false? You can be electrocuted by...
Oh, this is not by lightning. It's out of the question. Now that you know the answer,
The answer is true.
this is what you get from commercial TV. All right, so they said it's true, so which means that I'm sure they have a proof of someone getting electrocuted by lightning while driving.
Watch. You're about to see actual video of what it would look and feel like if it happened to you.
Oh! Oh my God! The car was just struck by lightning! Oh my God!
This young man from Colorado was lucky not to be electrocuted. The outer surface of his car took the hit, blowing out his tires as the lightning sliced through his car and into the ground.
What happened was it hit the radio antenna. It used to be right here. Big antenna going up about that high.
If you find yourself driving through a lightning storm, pull over and keep your hands on your lap. Don't touch metal like the steering wheel or the radio. That way, you'll survive this.
All right, let's go analyze it. All right, so the proof that you could be electrocuted by lightning is this, evidently. Number one, lightning strikes
in your car. The answer is true. Watch. You're about to see actual video of what it would look and feel like if it happened to you.
Oh! Oh my God!
The guy was shocked. Not physically, it was a psychological thing. Let's check to see how much the lightning penetrated into the car. Number one, the electrical systems are working fine because the windshield wiper is working. Engine is driving, so it didn't penetrate into the engine. The guy is talking, so he wasn't electrocuted. Electrocution is death by electricity, so that didn't happen.
Lightning! Oh my God!
What else? I see the clock, electronic clock, so there's no penetration of lightning into the electrical electronic.
Man from Colorado
And nothing happened to this guy. He was shocked. It was a psychological shock, not a physical.
was lucky not to be electrocuted.
He wasn't lucky. It's just physics. He wasn't supposed to get electrocuted.
The outer
As long as you're inside a metallic enclosure, we're perfectly fine.
surface of his car took a hit,
This guy is a storm chaser.
blowing out
That's the reason why the camera was running at the time.
his tires as the lightning
Tires didn't help. They went right through.
sliced through his car and into the ground.
What happened was it hit the radio antenna. It used to
Okay, so the antenna acted like a lightning rod in this case, attracted the lightning and it vaporized the antenna. It's completely
be right here. The antenna going up about that high.
If you find yourself driving through a lightning
And then a horrible advice. Yeah, so this is what's wrong with the commercial TV. They're getting better at it, but it's still horrible. Okay, they use a lot of common sense. A lot of these people, the writers, degrees in English or journalism or whatever, their understanding of physics is virtually non-existent.
storm, pull over and
They just spew out common sense. Okay, so you should be pulling over
keep your hands on your lap.
and then keep your hands on your lap.
Don't touch metal like the steering wheel
This guy was touching metal. He was touching the steering wheel. Nothing
or
happened.
the radio.
It's completely nonsense.
That way, you'll survive this.
You'll survive that because you're inside a metallic enclosure, and you will survive this 100% of the time. One of my students, a good student too, is 15 years ago, he misses one single lecture, and he said, "Ken, I missed the lecture," and he would never miss a lecture under any circumstances, with the exception of that one. And he said he had the most amazing excuse for it. I said, "What happened?" He was driving to school on that day. It was on a ramp, and all of a sudden there was a complete flash out. White out situation. It's just something flashed, and it was just everything was blindingly white for a fraction of a second. And then all of a sudden his car really slowed down, and then the engine was running, but the car was not driving or barely driving. So somebody pulls up next to him and said, "Dude, you just got hit by lightning." And then he got out of the car and looked at the car. It had 4 flat tires. All right, that's the reason why the car slowed down. All right, there was no sound. That's what he said. It was just a complete flash, and everything just appeared extremely white, and that was the extent of it. The guy didn't even realize that he got hit by lightning.
The monster created by a man they called Mad is turned loose to strike terror into the hearts of men.
Austin Richards is a self-described mad scientist. But tonight, he's going to play both Dr. Frankenstein and the monster at the same time. He plans to zap himself with 2 million volts of electricity, protected only by a homemade metal suit.
I've really been obsessed with the idea of being a mad scientist. The mad scientist knows exactly what he's doing, but at the same time, there's sort of an element of unpredictability to what he's doing. It sometimes gets out of hand.
Austin's interest in current events began when he was 14 years old. For a Halloween show, he built what's known as a Tesla coil, a machine that shoots fiery bolts of electricity through the air.
And that first Tesla coil made sparks that were about 12 inches long.
Tonight, Austin is unveiling his latest creation, 2 giant Tesla coils that can fire 2 million volts over 20 feet. But he isn't satisfied with just watching this dangerous light show. He wants to be part of it. Austin knows he could never survive a direct hit from the giant coils without some sort of protection. So he designed a special suit made of metal that would transform him into a human lightning rod. The idea for the suit first came to him at a restaurant, and he quickly scribbled his original design on a napkin. Eager to bring his creation to life, he went shopping for parts at the local hardware store.
So I started selecting bits and pieces of heating duct and dryer duct, actually trying them on my body, slipping them on my arms and legs, and I got some interesting comments from some of the people that work there.
That makeshift suit has now evolved into this, makeshift suit. And though he may not make any best-dressed lists, Austin hopes his suit will protect him from a 2 million volt direct hit.
What we're going to try is something that's never been tried before, which is to create almost, in a sense, double jeopardy, having 2 Tesla coils, suffusing a whole area with electricity, and I'm going to put myself right in the middle of it.
Austin's invited a select group of guests to witness this terrifying experiment. But are they going to see an electrifying performance or an electrocution? Austin begins by displaying the awesome power of the giant Tesla coils. He holds up a block of wood. It bursts into flames, but he's shielded by his protective glove. So far, so good. Next, Austin ups the stakes by raising up a solid steel wrench. It's bombarded by a barrage of bolts, but he's still okay. Now he's going to step right into this electrical storm and subject himself to 2 million volts of white-hot lightning. This scientist must be mad. If Austin's homemade suit should fail, he could be fried to a crisp.
If I haven't done my safety check properly, I could die.
He cautiously moves into position. The coils surge to life. Millions of volts of raw power pound his body.
The shocked onlookers can't believe what they're seeing. It only takes 100 volts to kill someone. So how could Austin survive 2 million? Incredibly, he's done it. Austin's electrifying experiment is a success.
I was really hoping that it was going to work, in the sense I was really hoping I wasn't going to get killed or injured. And I remember feeling a really deep sense of relief when the arcs began hitting him. I didn't feel a thing.
Beaming with success, Austin lights a cigar to celebrate. His crazy homemade suit actually works. Maybe this mad scientist isn't so mad after all.
It's alive! It's alive!
Okay, so here's a question for you. If you knew that you were about to be struck by lightning, and if you were to jump, would that prevent you from getting struck by lightning? The answer to that question is no. Okay, you don't need to be grounded for you to get struck by lightning. Airplane wasn't grounded, it got struck by lightning. This person is not grounded, still gets struck by lightning. Okay, so he's 100% safe because he's inside a metallic enclosure. This guy's a physicist like me. He knew he was going to be 100% safe going into it. He just put on a show, and he did a good job with it. Okay, so as long as you're inside a metallic enclosure, in this case, called Faraday's cage, it's the same thing, Faraday's cage. Any enclosure, Faraday's cage. Okay, so those of you guys who love conspiracy theories, and those of you guys who believe in conspiracy theories, one of the theories been out there forever, ever since early 2000s, is the theory that we've never been to the moon. Okay, one of the arguments is, how can you survive radiation in space, radiation of charged particles in space? All right, so that's one of the things that I keep hearing. So this question is based upon that conspiracy theory. All right, so pick out the best answer and put it in the chat. Okay, so the best answer is gonna be, this is complicated. All right, guys, the radiation due to charged particles in space, and the charged particles in space is the problem usually, can be contained because the net charge is gonna remain outside of a metallic enclosure, right? So the best answer is gonna be C. There you go. Okay, so a couple of things that we need to discuss. Number one, the excess charge, the net charge, is gonna reside on the surface of a conductor, which means that the electric field on the inside is going to be 0. So there's absolutely no electric field on the inside. So which means that the conductor or the enclosure, metallic enclosure, is going to shield any electronics on the inside from electric fields created outside of the conductor. So which means that if you have any sort of sensitive electronics, if you want to protect the sensitive electronics from any sort of electrical discharge or any accidental discharge or zapping from outside, that would destroy the electronics. What you need to do is you need to take that electronics and you need to place it inside a metallic enclosure. So examples of this, my laptop computer, my desktop computer, anything that has sensitive electronics is usually contained within a metallic enclosure or a cell phone to a certain point. So you got sensitive electronics, just place it inside a metallic enclosure. All right, so pick out the best answer. Okay, so out of the 4 answers, the best one is going to be B. Electric field on the inside is going to be 0. All right, so this thing is about 2 minutes long. Okay, so what I want you to do is, this is from the Discovery Channel being a commercial TV. Something is going to be horribly wrong somewhere within this video. So what I want you to do is I want you to figure out what's wrong with one of the explanations.
When a thunderstorm forms, people's lives can be at risk.
We tell people when thunder roars, go indoors. What we mean is seek a safer shelter.
If you're ever caught out in a thunderstorm, one of the safest places to be is in a closed vehicle.
Many people believe the rubber tires on a car will keep them safe, but that's not true. It's the car's metal body that provides protection, as this high-voltage experiment will demonstrate. A Tesla coil is the lightning simulator, an electrical transformer that discharges 3/4 of a million volts of electricity, more than enough to kill. Dr. Lisa Lazarek is an electrical engineer who's willing to sit in a car underneath the coil to prove that the metal body will protect her.
The electrical charge striking this car is going to conduct around the outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car. But it's one thing to talk about the theory, and it's another thing to put it into practice. So I guess I'm ready.
The electrical charge flows around the metal body of the car and discharges harmlessly to the ground.
I'm fine. The theory has worked as expected. My feet are slightly tingling, and because I was nervous, my hands are still clamped together. But other than that, I'm fine.
Okay, so this was actually better than what I anticipated, so which means that commercial TV is getting better. Except there's one statement which was completely wrong. Okay, did anybody figure out what's wrong with what was being said?
She said you were fine as long as you don't touch the metal, when in reality you could still touch the metal on the inside of the car.
100, all right, give yourself 20 points to them. Absolutely. Okay, it's sad part of it is she's an electrical engineer. She's got a PhD in electrical engineering. Engineering is applied physics, and she still does not understand one of the fundamental facts about physics. Okay, so I will blame the Discovery Channel for it because NOVA would never make this mistake. The quality that they hire for NOVA, they usually get the best of the best researchers. Commercial TV is still mostly for entertainment. Okay, the fact that they end up getting an electrical engineer is kind of weird. Why not get a physicist?
The theory has worked.
You can't touch the inside of the metal. You can lick the inside of the metal. She almost gave herself a heart attack.
Touch the metal.
You can touch the metal on the inside.
The outside surface of the enclosed body, so I should be fine.
To prove that the metal body will protect her.
The electrical charge striking this car is going to conduct around the outside surface of...
I mean, she knows the facts. It's going to conduct around outside surface. That implies that she doesn't make the connection that means that the charges cannot get inside.
Body. So I should be fine as long as I don't touch the metal.
Okay, so mental connection is not there. So she could probably do the math, but she doesn't have a good understanding of what's going on. She can touch the metal on the inside, she's fine. It's going to be 3 million when the lightning happens. All right, so the first thing that happens is the charge will become separated inside the clouds. Top is again positive charge, bottom is again become negative charge. The Earth, which is initial negative charge, will become polarized, it becomes positive charge. And now the electric field is pointing towards the clouds from the ground. Negative charge will start to move towards the ground. The positive charges, ions, will go up when they meet the lightning is born. Okay, so here's the strength of the electric field during a lightning storm. All right, so determine the net positive charge pulled to the Earth's surface within a 1 square mile area during a lightning storm. Okay, so that's the first question. All right, so we're going to be looking at the strength of the electric field within this region expressed in terms of square meters. All right, so if you're looking at the area, 1 square mile area, so what's the net charge within that region? Now, Gauss's law is useful for this sort of stuff. All right, let's figure out the net charge contained within that region. Okay, so isolate Q by dividing both sides by epsilon naught. Okay, so we know the value of the electric field, we know the region. Okay, so what's the net charge within that region? All of a sudden, you can come up with a number for it, so that's a nice mathematical exercise. Vectors, metallic enclosures in general. Net charge will always remain outside, which means that the electric field with that is going to be 0. If you're trying to shield any sort of sensitive electronics, you will place it inside a metallic enclosure so that it doesn't get fired by accident. Like, I don't know, it's some kind of an accidental spark. Because the electric field on the inside is going to be 0. Sensitive electronics, like the sort of electronics that the computers have, or your cell phone has, or whatever. All right, so sensitive portions of the electronics will always be enclosed within a metallic enclosure. All right, that's too many enclosures. Okay, another thing that I want to notice is charge distribution is not necessarily uniform on the metal. So the charge distribution depends on the shape. Notice that when the edges are pointy and then this one is flat and this is pointed, it's going to have a larger charge concentration, which means that the sharp and pointy edges will have a larger charge density, right? Concentration of charge is the charge density or whatever. Okay, so we're still dealing with electrostatics, otherwise known as static electricity, which means that ideally we're dealing with a situation where the charges are not in motion. Right? The reason why the charges are not in motion in this case is because the net electric field, which is going to be parallel to the surface, is going to be 0. Once the charges get repelled to the surface, they will get repelled away from each other until the charges stop moving, which means that the net force acting on these charges will be 0 at some point. Okay, which means that the component of the electric field, which is parallel to the surface, is going to be 0 at that point. So in that way, we're not getting any electric currents. And the only surviving component is always going to be perpendicular to the surface. All right, and take a look at this. This is even more obvious. All right, so notice that the charge concentration is much larger. So because this area, this is much sharper. So as a result, what's happening here, within this region, we end up getting a much larger charge density. Okay, so whoever the artist is, end up drawing these electric field lines. In reality, because of the fact that the charge density is larger here, the strength of the electric field would be much larger. This is going to give you a much larger electric field strength. Okay, so during lightning, if you're carrying something which is really pointy or it's got sharp edges, around the sharp edges and around the point, the charge density is going to be larger, which means that the electric field is going to be stronger, so it becomes much more attractive to lightning. All right, so that's the idea behind the electric field.
Basically, you have but the deadliest repel there is a slightly negative choice.
Okay, we've discussed that before, so we did that problem. I don't want to redo that. Okay. All right, so the lightning rod is the stuff that we were discussing last time.
It's still today the best way to put
down a wire. Franklin revealed be his gift to the world.
All right, so the purpose of the lightning rod is to attract lightning to the sun.
The ordinary lightning rod, the Franklin rod, is still
and
the basis of the lightning protection code in every single country in the world. It's still today the best way to protect an ordinary house or a structure from lightning damage.
All right, so one of the things that I want you to notice is you got a ball here, which is kind of interesting. And then when you start to go up, higher up, notice that it becomes edgy and it becomes sharper. All right.
Calming the odor of lightning, this frightening thing, this had a huge impact on the public imagination. There was an episode, for example, with two ships side by side. One had a lightning rod, one didn't. Both struck by lightning, one destroyed completely. The one with the lightning rod, perfectly fine. First, the clergy felt that he was usurping a prerogative of the Almighty. Franklin said, well, we do not hesitate to protect ourselves from the hail of heaven with roofs and shields. So we should be entitled to do the same with lightning.
In an age of reason, is proof that the lightning discharge is an ordinary natural phenomenon and not a manifestation of the powers of darkness or the force of an angry god, was seen as a tremendous blow for reason against superstition.
In 1753, Franklin is awarded the Copley Medal, the 18th century equivalent of the Nobel Prize for Science. This once runaway printer's apprentice is now the most famous American in the world.
All right, so far Franklin's contribution to physics is he was able to explain the attraction and repulsion phenomena regarding charged objects, introduced two different charges into physics, positive and negative. So he was able to say that the repulsion is caused by like charges repelling, and the attraction is going to be caused by unlike charges attracting, and that's it. All right, so, and then he gave us the lightning rod, in essence. Okay, so speaking of the lightning rod, does metal attract lightning?
Overcoming the damaging effects of
Okay, guys, give me some feedback.
one lightning strike can be hard enough, but a few rare individuals, like Park Ranger Roy Sullivan, are proof that lightning can strike twice and more. His daughter remembers his first strike.
Okay, have you seen this video last time? Yes or no?
I think we saw like part of it, but you didn't like. I didn't guess we didn't fully watch
Oh,
it.
okay,
Or something. I
we
don't
didn't.
quite remember.
Okay, so this guy's gonna get struck by. Okay, I remember where we were. Yeah.
This is from the first one. That's in 42, and lightning went through his watch. You can see it has a hole through side to side.
For 27 years after this first strike, Roy was untroubled by lightning until one fateful day in 1969. A side flash bounced into his truck, hitting him in the neck and burning his head. The odds against Roy being struck a third time were over 1,000,000,000 to 1, but only a year later, near his home, lightning hit a transformer and arced to his left shoulder. But this was not the end. In 1972, while taking refuge from a storm inside a mountain station, Roy Sullivan was singled out for a fourth time.
I recall Roy having lost all of his hair on his head. He also had a burn around his ankle that was, I would consider, substantial.
Come on, Rick. How are you, Roy? Pretty good. Working a lot today? Sure am. Have a good one, too.
By 1973, Roy had taken to carrying a bucket of water with him when he made his rounds, in case he caught fire again. Even though he tried outrunning the thunderstorms, in June 1976, Roy was struck again for a record 6th time. And his troubles weren't over yet. The following year, while out fishing, Roy was struck for the 7th time, and he became known as the human lightning rod.
People have called him that before, human lightning conductor, but I don't know. I don't know if it was a chemical mineral in his body. He said that before.
Roy was worried that metal on his body might be attracting the lightning.
He didn't even wear a wedding ring or a watch because of that. He didn't wear those.
Belt buckles and metal zips fuse and melt after a lightning strike, and many lightning survivors have terrible burns for metal objects that they were holding or wearing. But does metal on the body actually attract lightning? At a high-voltage lab in Manchester, England, researchers are preparing to find out.
We use an impulse generator, which is charged to a voltage of approximately 1.5 million volts, causing a simulated lightning bolt. Mannequins have been painted with an electrically conductive paint so that they simulate the resistance of the skin of a human under normal conditions.
Various metal objects have been attached to the test dummy on the left to see if it will be struck by lightning more times than the one on the right.
He takes the first hit. Takes the second one. Takes the third hit. Finally, she gets it. Look at his ring. I think he's got some metal pumps at home.
In this test, the dummy without metal was actually struck more often than the one with metal.
Okay, so what does that mean? That means that it's random. Metal in your body shouldn't be attracting light.
Just like a real lightning strike, the electrical flashover has left telltale fractal patterns on the dummy's body. If Roy Sullivan did have any metal on his body, it should have had no effect. Lightning experts believe it was due to a combination of high exposure and bad luck.
Roy Sullivan was outdoors in an area with quite a bit of lightning. He was exposed to the lightning a great deal, more than most people are. The visitor is maybe there for a few hours or a day or so. He was there for many years, and that cumulative effect catches up with you.
All right, so a couple of...
Overcoming the damaging effects of one lightning strike can be... For 27 years after this first strike, For 27 years after this first strike, Roy was untroubled by lightning until one fateful day in 1969. A side flash bounced into his truck, hitting him in the
All right, so would you ever get struck by lightning inside a car?
neck and burning his head.
The answer to that question is no, provided that you have the windows up, right? All right, so make sure that they're up.
You lost today?
To his left shoulder, he called. But he had a mountain.
I don't know how many of you guys seen the movie A Curious Life of Benjamin Button, or Case of Benjamin Button. I forgot the name of the movie. There was a secondary character in the movie, and every time the camera was focusing on him, it was talking about getting struck by lightning. And then every time he had a different version of it. All right, so and then in the movie, I think he got struck by lightning 7 times. It's based on this guy's life.
Roy Sullivan.
This guy also got struck by lightning 7 times.
Mineral on his body. He said that before.
So the question is, metal on your body attract lightning? All right, so a lot of you guys will probably thought that not very likely because of the size of the metal. So that's one of the things that the Mythbusters investigated. All right, so let's talk about rolling out the window during a lightning storm. Okay, so why is it that you have to roll out the window? All right, so lightning usually happens whenever the step leaders from the cloud make contact with the streamers from the ground. All right, so positive charge is going up, negative charge is coming down. And obviously when they make contact, when they meet, you end up getting this electrical discharge. All right, so these step leaders are going to come from the clouds, and streamers, your body's going to start to produce these streamers. The best thing to do is you have to sever that connection. And how do you sever that connection? Just put an insulator between. The glass is going to be just fine. Okay, so there's no way these charges will be able to contact with the streamers from your body. At that point, you're safe. Roll up the window. Don't leave a gap in between during an electrical storm.
Maybe.
So the next question is, how about the size of the metal?
Even more.
Size of metal.
More metal. Of course.
On your body.
If your tongue piercing is this big, lightning is the least of your worries.
Let's not go into the top of the head and go out to the bolt and back in.
It just goes to show, don't put any really big bolts in your mouth during a thunderstorm.
Finally, a test for the mother of all studs.
Oh, cheek piercing there.
It's unlikely to catch on at many nightclubs, though it might just help you get in the door. Will it attract lightning? At last, a direct hit.
Well, that knocked the doorknob right out of his face.
Okay, so if you go with Mythbusters,
will it attract light?
All right, the conclusion is the size of the metal on your body. All right, so if you have a doorknob on your face, more than likely you're going to get struck by lightning. That's what they're trying to say. All right, guys, the Mythbusters, one of my favorite shows on TV. These guys are not physicists, they're not engineers. These are special effects artists. Okay, sometimes the conclusions are way out, and this is one of those instances. Okay, so it's not the size of the metal that matters, it's the shape of the metal that matters. Okay, when you have sharp edges, or if the metal is very pointy, around the pointy edges and sharp edges, the charge density is going to be larger. Larger charge density is going to create a stronger electric field. As a result, the metal is going to become more attractive. Lightning rods, you notice that they are extremely pointy and they're going to be extremely sharp. Okay, when I say sharp, I should say pointy, which means that when they become polarized, they generate a very strong electric field within this region. As a result, they initiate lightning in essence, because you don't want the building to get hit. You just want the lightning rod to get hit so that you could take the electricity to the ground immediately. That's the whole idea, so that the building is protected. All right, and you want to make it you want to make it as pointy as possible. You want to squeeze as many charges into that point as possible, so that the charge density goes up. As a result, it generates a very stronger electric field to attract the lightning to itself. So that's the whole idea. So that's the design that. All right, so it looks like this. This is a beautiful design. And then notice that you got the additional sharp pointy edges. The whole idea is to initiate lightning by attracting the lightning to itself. So that's the design that Franklin came up with. And Franklin came up with it, and he didn't even patent it. He said, hey, just use it, all right, for safety purposes. And King George said, no, I'll do better. I decided to come up with a spherical design. Okay, so what's wrong with this spherical design? What's wrong with this spherical design? And notice, okay, I just saw it right here. Okay, guys, notice that this top is pointed. Spherical design, meaning that it's going to have a uniform charge distribution, which is fine. So it's going to get polarized or charged in that case. And then it's going to be attracted to lightning. But because the charges are uniformly distributed, the strength of the electric field is not going to be as intense as the strength of the electric field around the pointy edge. Okay, so it's not going to be as attractive to lightning. All right, so why did the king decide to come up with a competing design instead of using Franklin's design? The reason is because Franklin had everything to do with the reason why Britain ended up losing colonies. All right, he knew that the Franklin was behind that. He knew that the Franklin played a major role. And England ended up losing the colonies under King George, just a personal animosity. So that's the reason why. The nice thing about King's design is, it doesn't work as well. All right. So if you have some kind of a spherical metallic ball on top of something that you're trying to protect yourself from lightning, I'm talking about the car antennas, for example. All right. If you look at the car antennas, all car designs, you will notice that there's a ball, a spherical ball on top of it, metallic ball on top of it. Once again, you will see the same thing on top of the flag poles. Okay. So they just want to make sure that the top of it doesn't have any sharp edges or corners, because you're trying to protect it from getting hit by lightning. So the King's design, because it didn't work, all of a sudden it gives you some protection in a different surface. So that worked out. All right, so once again, the German military helmets, World War I, you got the spike on top. The idea was, obviously, for whatever reason, if you run out of bullets during a battle, you can just ram down the enemy. But then again, if there's an electrical storm, they notice that they end up losing soldiers because of it. They were getting struck by lightning. So this is a lightning rod in essence. It's not the metal itself that's attracting lightning. It's just the spike on top. So World War II, Germans learned from World War I. They said, okay, just keep the helmet as it is, because it's not going to attract lightning to itself, as long as you get rid of this. So that worked out beautiful. All right, so the spike is going to have a much larger charge distribution density at the peak, the point.
In the middle of a children's
The other thing that I want you to notice is how much umbrella designs change.
soccer game, the skies open. Players take shelter under a
All right,
tree,
so
and
I don't think they
the
sell
coach puts up a large umbrella. It's a
this.
terrible mistake.
The top used to kind of point it. Now they don't make them pointy anymore because it becomes attracted to lightning. And then they make sure that the edges are not sharp either. Okay, so if you have an umbrella, you don't want to be attracting lightning.
17 people feel the force of the lightning strike. But how could so many have been hit by a single bolt? Most victims are not hit by lightning directly, but by a charge that jumps from a nearby object, such as a tree. This side flash still has enough power to stop the heart and burn the skin. Victims can also be shocked from below. Immediately after a strike, the ground becomes electrified. The current travels through the person where they make contact with the ground, usually up one leg and down the other.
All right, so majority of people survive because those are side flashes. The ground becomes electrified, meaning that keep your feet together. Why? You'll find out next week. Don't ever lie down on the ground. Once again, why? We'll find out next week.
If you're caught out of doors in a thunderstorm, the best thing to do is get indoors in a sizable building. If you can't do that, you should get into a metal car.
All right, so this is going to be your test question. Which one is better, a sizable building or a metal car? This guy says the best thing to do is to get into a sizable building.
The car's metal body discharges the current away from the driver and below.
Ever stand under the tallest tree, try to stay off hills where you're the tallest object.
But you're not totally safe indoors.
If you're indoors, you shouldn't touch anything that's connected to the outside because the lightning could strike that outside and come in. And that includes the telephones with wires.
All right, so now he's going to qualify. Sizable building is the best, he will say. But at the same time, just stay away from everything which is connected to the outside, such as well. Don't be on the phone, obviously, if it's got a landline.
Be leaning against the refrigerator.
Don't be getting anything from the refrigerator.
Shouldn't be near the house plumbing.
All right, stay away from the plumbing, so don't be pissing or crapping.
Shouldn't be in the shower.
Don't be in the shower.
Just stay away from everything.
Stay away from everything. So just a generalized blanket statement. Stay away from it. Guys, in your car, you can piss and crap. It doesn't matter. You're still going to be safe. So the safest place to be, literally, is inside a metallic enclosure. Car, airplane, whatever. All right. Be on the inside of a metallic enclosure. The buildings, they're safe, provided that the lightning rod is going to do its job. The lightning rod is there to attract lightning pieces, but it may not succeed 100% of the time. Sometimes the lightning misses the building completely, and misses the lightning rod. And the building sometimes gets. If that's the case, you know the skeleton of a building is made up of metal, so all of a sudden the entire building becomes electric. And then people will get struck by lightning as a result.
Amazingly, all 17 victims survived.
All right, so most do survive somehow. All right, so okay, so this is an insulator. So this is a non-conducting sheet, so it's an insulator. Notice that it's charged. The surface becomes charged, and in this case, it is charged positively. So the electric field is pointing in this direction. The area vector is pointing in the same direction. The electric field is pointing to the left. The area vector is pointing to the left. And the stuff that you guys are looking at, this thing is your Gaussian region. Right? So you draw your Gaussian region just like this. All right, so that's what we will do. So we'll do a fast derivation. This derivation is going to be really fast. Gauss' law is just amazingly powerful in terms of computing something like that. This is simple enough geometry. All right, so here's the insulator. It's a charged disk or some kind of a sheet, and it's going to be positively charged. So this becomes the source of the electric field. So the electric field lines are going to be pointing to the left as well as to the right. And then what else do we have? We also have the area vector pointing in the same direction. All right, so the area vector is a vector which is perpendicular to the area. This is the same as the normal. The surface that we were dealing with in physics 1. All right, so what do we do? In order to figure out the strength of the electric field, what we do is we do a Gaussian. Just look at a certain region, so I'm going to draw my Gaussian here. This is my Gaussian surface. And the only stuff that I'm going to be interested in is the strength of the electric field intercepted by the ends that you're looking at. All right, so you're looking at the area here, you're looking at the area here, and you're looking at the area here. That's intercepting the electric. All right, so let's try to do this. So according to Gaussian, this is what we use. The net charge on the inside is going to be responsible for the electric field. And so what that means is you're looking at the circle here, which says that just integrate it in the counterclockwise direction. So here's my region, so I'm just going to integrate this region that you're looking at in this direction. All right, so there's nothing happening in this region, and there's nothing happening in this region. All right, you have an area vector in this direction that's perpendicular to the electric field, so it's not going to contribute. There's an area vector which is perpendicular to the electric field, it's not going to contribute. Okay, so you can just traverse in this direction. So if things start to happen right here, notice that the electric field and the area vectors are in the same direction. So that's what I'm going to focus on at this point. So E and A represents the magnitude of the area on the right. So I'm dealing with this portion of it. And then nothing is happening in this region for the reasons that I explained. So area, once again, is 90 degrees to the electric field, so it doesn't mean anything. So as I'm traversing it in this direction, I get to this point. Notice that the electric field as well as the area vectors are to the left. So I keep on with my summation. So the electric field is to the left. The area is also to the left. So the entire summation, the intervolution summation, is going to equal to the net charge on the inside divided by the epsilon naught. All right, so the net charge is the charge that we are dealing with here. So that's the net charge. Yeah. Okay, so this is straightforward. Negative times negative is going to be positive. So what do we have? We will have 2 times 3 times A equaling net charge divided by 0. All right, solve for the strength of the electric field. And when you solve for the strength of the electric field, obviously, you divide both sides by 2 and then A, and that's what we're doing. So the strength of the electric field is going to be Q divided by 2 epsilon naught A. And what does that mean? What that means is the following. So this is the net charge distributed over this area. So what does that represent? It represents the charge density, surface charge density. So the net charge distributed onto the surface area is going to give you the surface charge density. All right, so do a back substitution. And you are done. That's it. Straightforward. It's easy math, easy work. All right, so this is the strength of the electric field of a charged insulating sheet. All right, the mathematics is straightforward, but math is not physics, guys. All right, so math is not physics. All right, so this is how you do the math. Okay, so having said that, here's a really tough question. If it's metal, electric field on the inside is going to be 0, right? All right, can you figure out the strength of the electric field on the outside? All right, so this has to be some kind of a metallic enclosure. That's the reason why the strength of the electric field is 0. Or it could be a piece of metal, it doesn't matter. Inside the strength of the electric field is going to be 0, so the net charge is going to be on the outside. Okay, so the mathematics is going to be exactly the same as before, so I'm not going to repeat it. I'm just going to cute. All right, so the work is already here. So this is for a non-conductive sheet. All right, so this is the one that we've been discussing. All right, so what we have, so you got the net charge located right here. So this is subject charge Q that you're looking at. So this is the work that we just did, and this is the result that we came up with. Okay, so what if it's a metal piece? It's a piece of metal. So if it's a piece of metal, what is the electric field strength of this piece of metal? Okay, how do we do that? Oh, I was hoping that I had that. Okay, oh, I have it here. Q. All right, so it's the same idea. All right, so this is a metal piece. Inside the strength of the electric field is 0. So the net charge is going to be on the outside. So you put your Gaussian right here. And when you place your Gaussian right here, so what you have, when you place your Gaussian right there, all right, so the net charge on the inside is going to be right here. All right, so your net charge is right here. So that net charge is going to be responsible for the electric field in this direction, and the area vector in this direction. Electric field is from left to right, it's in this direction, and then so the area vector here is perpendicular to the electric field, so it's not going to have any contribution. Once again, it's the same rule. You do your integration in this direction, in the counterclockwise direction. You will find the contribution only within this region. So notice that within this region, you have the strength of the electric field times the area. That's what gives you your flux. And here's the net charge on the inside. All right, so isolate E from here. When you do that, this is the formula that you come up with. Q divided by A is going to be your surface charge density. And here's the formula that you come up with. Surface charge density divided by epsilon naught is going to be the strength of the electric field of a charged metal. That's it. The weird thing is if it's a flat surface just like this one is, notice that this is a flat surface, the charges will be uniformly distributed on the surface. So if it's a flat surface, the charges will be uniformly distributed, which means that the strength of the electric field is going to be constant, only for a flat surface, just like that. All right, so I'm talking about capacitors. Here's what I'm talking about. This is a parallel plate capacitor. Notice that this plate is getting positive charge. You're dealing with a flat surface. This region is flat. So which means that the charges will be uniformly distributed. What that means is the electric strength of the electric field is going to be uniform. So if this is uniform, if the charges are uniformly distributed, the electric field strength is going to be constant. Got it? So this is your capacitor. And inside a capacitor, the strength of the electric field is going to be constant, provided that you have these flat, smooth surfaces. And that's what you have. All right, so this is an expression that would come out of math. So the question is, why would the strength of the electric field be constant on these flat surfaces? That would be your test question. Okay, strength of the electric field will be constant if the charges are uniformly distributed, which means that the charges will be equidistant to each other, right? That's what it means. And which means that the strength of the electric field due to these charges parallel to the surface will cancel out. The components of the electric fields parallel to the surface will cancel out. Only surviving component is going to be the perpendicular component. Okay, so the shape of the tip of the lightning rod is going to matter because the sharp edges as well as the pointy edges will have a much larger charge density, right? Okay, so based on the last one that we came up with, what happens to the strength of the electric field when you increase the charge density? When you increase this charge density, what happens to the strength of the electric field? The electric field is going to get stronger, right? So it becomes more attractive. Charge density around the shape, around the sharp edges as well as the tip is going to be much, much, much larger, which means that the tip and the sharp edges tend to be a lot more attractive to lightning because the strength of the electric field is going to go up. The electric field is going to get stronger and stronger near the sharp edges as well as the tip. All right, does metal on your body attract lightning? It's not the size of the metal, it's the shape of the metal that may attract lightning. Okay, so you don't want anything which has sharp edges or which are in the point. So that's what you need to avoid in terms of attracting lightning. Question number 10, does the strength of the electric field change within a capacitor or does it remain constant? Inside a capacitor, charge density is going to be constant on the metal piece as long as it's flat. So, which means that the strength of the electric field is going to be constant. All right, it's towards the middle. If these are infinitely big sheets, obviously it's going to be constant all the way through. But because of the fact that these metal plates have finite sizes, around the edges it's not going to be constant, but towards the middle it's going to be fairly constant. But we don't have to worry about that in this class because this is still a freshman level. Okay, so this is good enough. All right, so what's left over? There's one more concept left over before we jump into the next discussion. So if the charge distribution is constant, the charges are uniformly distributed, the strength of the electric field is uniform. So inside a capacitor, the strength of the electric field is going to remain constant. That's what it means. If the strength of the electric field is constant, then if you place charges here, they're going to experience a constant acceleration, constant force, constant acceleration. So their motions will be uniform. All right. Problem number 6. Okay, so we're looking at the nucleus of the gold atom. I don't want to do this numerically, but there's a derivation that I want to use that you will need in solving problems on Sunday. Okay, so this is the last topic that we will get to treat in this one. All right, so what do we have? We got a nucleus atom. It's got a radius. The radius is known. It's 6.2 times 10 minus 15. All right, so that's 10 to the minus 15. So that's the size of the nucleus. It's got a net charge. Z is the number of positive charges of the protons, so it's going to be 79. So the net charge is going to be positive. So it says that to plot the magnitude of the electric field from the center of the gold nucleus outward to a distance of about twice its radius. All right, so what happens to the strength of the magnetic field when you start to plot it from the center of the nucleus all the way to the outside, almost twice the distance of its original radius? That's what it is. All right, assume that the nucleus is spherical and the charge is distributed uniformly throughout the volume. All right, so how do you do a problem like this? All right, so let's come up with a nucleus. Okay, so case number 1 is the first one that I'm going to look at. This is going to have a nucleus, so R is going to represent the nucleus of this. Okay, so we got a uniform charge distribution on the inside. So assume that this is uniformly distributed, so the net charge is going to be on the inside. The first thing I'm going to do is, this is case number 1, I'm going to place my Gaussian on the outside. So I'm going to place my Gaussian right here at a radial distance of lowercase r. That's where it's going to be. So I'm going to mention that in my case number 1, R is going to be larger than capital R. So what I'm interested in is the strength of the electric field outside of this region. So that's what we're going to figure out. So what is the strength of the electric field in this region? Remember, the net charge on the inside is going to be positive, so that positive charge is going to be responsible for generating the electric field. All right, so the electric field is going to be radiating away from the nucleus. That's what it is. All right, so how do we do this? The case number 1 is kind of straightforward, and that's the reason why I picked that one. This is more of a warm-up. So strength of the electric field times the total area of the sphere that you're looking at. So this is for a sphere, is going to depend on the net charge on the inside divided by epsilon. All right, so we know something about the area of a sphere. All right, so it's a nice symmetry. So the area of a sphere that we get to use is going to be, what is it, 4 pi r squared. All right, one of the things that you guys will struggle if this is a new concept for you, and it is, I want you to notice that this r is always the r for the area. Then you're always dealing with the area of the Gaussian. All right, so don't get them confused. All right, this capital R is the radius of the nucleus, and lowercase r is always going to be the Gaussian. All right, in this case, it's going to be fairly clean, but in the next case, if you're not careful, things can go to hell. A lot of students get confused about that. All right, so this back substitution, it gets back substituted. Now what do we have? So now we got 4 pi r squared, all right, and then you got the strength of the electric field, so net charge divided by epsilon naught, and this is going to give us an expression that we're looking for. So divide both sides by 4 pi r squared. All right, so by dividing both sides by 4 pi r squared, all right, so you got your cancellations, these are going to cancel, and then we're done. All right, so we got our expression. So what do we have? Net charge divided by 4 pi epsilon. All right, and then your variable is going to be r, so this is going to be r squared. All right, so this is outside of the region, so immediately I can graph this. All right, so now we are outside of the radius. So here's the strength of your electric field. It's a function of r, and this is your radial distance. So on the outside, what you end up getting is you got this inverse relationship. All right, E is going to be inversely related to r squared. So what that means is electric field strength is going to be inversely. So outside, that's what you end up getting. All right, so this one was easy. All right, so which means that the nucleus is going to act like a point charge if you're looking at it from outside. Okay, case gets slightly complicated. When I say slightly, I mean slightly. All right, if you're not careful, you will get confused because of the symbols. The reality of it is this is straightforward math. All right, so case number 2. Now what we'll do is we will go into the nucleus, and then we'll take a look at what happens. All right, so case number 2. Okay, so this is my nucleus. One more time. All right, so this is the size of the nucleus. So what I'm going to do this time is I'm going to place my Gaussian on the inside because I want to see what happens on the inside as I'm increasing the distance, radial distance from the center all the way to the edges. So this is the distance that I'm going to keep increasing. Okay, so R is going to locate the Gaussian surface one more time. All right, so this is our case number 2. And in the case number 2, R is going to be smaller than the radius. And then we will be looking at the strength of the electric field on the inside. All right, once again, the mathematics is the same as before. Okay, so net charge is once again fixed. But, okay, so, okay, now the stuff that I need to clarify. Q naught is going to be the net charge inside the Gaussian. Okay, that's what we're going to be focusing on. So the only difference between the previous one, this one was the net charge inside, this one was the net charge inside the nucleus. All right, so this is the net charge inside the nucleus. This is the net charge inside the nucleus. Here, Q prime is the net charge inside the Gaussian. All right, so before we forget, let me just clarify that. So when you guys go back and refer back to your lecture notes, you'll remember. So this is the net charge that we're looking at inside the Gaussian. All right, so you need to make that distinction. So this is the net charge inside the Gaussian. So the net charge inside the Gaussian, in this case, I'm going to use blue. All right, strength of the electric field is going to change as you start to increase the area of the Gaussian. That's what it means. All right, so the strength of the electric field is going to depend on this radial distance that you're looking at. All right, I'm using R prime there. Maybe I shouldn't. So let's use R. All right, so R is good. Let's use R. Okay. So R is going to vary. All right, so now let's go back and finish up the problem. All right, once again, flux is going to be caused by, flux by definition is the amount of electrical field intercepted by area of the Gaussian. And that's going to depend on the net charge within the Gaussian surface, which is Q prime divided by epsilon. All right, and once again, we're dealing with spheres. And once again, we're using a symmetrical geometry. For a sphere, it's always going to be 4 pi r squared. All right, so this is the area of the Gaussian once again. It's going to be intercepting the electric field. All right, we'll do a back substitution. And isolate E from here. And when we isolate E, the equations will look identical. Ooh. All right, and then I will stop right at this point. All right, this is as far as we're going to get. So, all right, so this equation looks like this again. All right, so both these equations look the same. All right. They look alike, except there's a slight difference. All right, so just want to get this reading. All right, so what's the difference? Okay, guys, what's the difference between these two equations? The difference is this. This is the net charge. This is the net charge inside the Gaussian. This is the net charge of the nucleus. This is the net charge inside the Gaussian. All right, so what you need to do is you need to express the net charge inside the Gaussian surface in terms of the net charge inside the nucleus. Got it? In order to get the complete expression. So this net charge inside the Gaussian needs to be expressed in terms of the net charge of the nucleus. All right, mathematically, I'm going to do a little bit of mathematical bullshit, right? What we need to do is we need to express the net charge inside the Gaussian in terms of the net charge of the nucleus. So the net charge inside the Gaussian, which is this, has to be a function of the net charge. And then you need to plug this into that. So how do we figure out the net charge inside the Gaussian in terms of the total net charge? What do we do? Any suggestions? All right, so how do we express the net charge inside the Gaussian in terms of the total charge? Okay, guys, the only way you could do that is if you remember the assumption. What is the assumption? Assumption is, the assumption that I underlined before. Charge density should be uniform. All right, or else good luck solving this one. So the volume charge density has to be uniform. All right, so with this assumption in place, in total, yeah, you can solve this problem. This is a huge assumption. All right, so I want you to remember this assumption. So the charges are uniformly distributed. If the charges are uniformly distributed, I love doing this. And now you can solve this problem. All right, so if the charges are uniformly distributed, then you can solve this problem. All right, so what do we know? Charge density means the net charge divided by the volume. All right, so V here is the volume. All right, so this is the volume of the sphere. So that's the net charge. So the charge density of the volume of the nucleus has to be the same as the charge density within the volume of the Gaussian region. Gaussian. Got it? All right, so the volume of a sphere, regardless. What is the volume of a sphere? The volume of a sphere is going to be 4 pi r cubed divided by 3. All right, so here's a generic expression for it. So what we will do is just slide the generic expression here. Okay, so all right, so here's the generic expression. So just apply it to both of them. All right, so that's what we will do. Okay, so what I'm going to do is I'm going to grab this term and then isolate Q naught. That's what I'm going to do. So here's the active quotient of the formula. All right, so let's grab Q naught, Q prime, and then simplify. All right, so Q prime in this case is going to be Q divided by V prime divided by V. All right. Now write out the expression. V prime is the this is the volume. So this is going to be 4 pi r Q divided by 3. And V is the volume of 4 pi r Q. Okay, so capital V is the volume of the. All right, the rest is kind of straightforward at this point. Electrons will cancel. And then what do we have left? So we come up with an expression for Q prime, which is going to be r cubed divided by the cube of the radius of the nucleus. All right, and then all right, so let's substitute everything into that. Okay, so this is going to get substituted. This gets substituted into that. And as soon as we do that, we're done. All right, so strength of the electric field. as a function of the radial distance. This would be your expression K, the strength of the electric field. And Q prime is going to be expressed in terms of Q, so I'm going to place my Q here. And what do we have? We have R squared, and then we have R to the third power, and then we have, I lost connection on that. So immediately, we got our cancellations. This is the third power, this is the second power. Right? So you get your cancellation. So I'm going to move this here, and as a result, what do we have? So this and these will cancel, and that's it. We're done. So its strength of the electric field as a radial distance is going to be Q divided by 4 pi, capturing that, divided by I cubed, and then you have your R. So what that means is, within the radius of the sphere, strength of the electric field is going to increase radially. That's it. So you increase the radius, this goes up, the strength of the electric field is going to go up. All right, so what that means is, if we copy this, come up with an expression. So all the way up to the radius. All right, so this expression means that the strength of the electric field is going to be directly proportional to the radial distance, so this thing's going to go up just like that, and then it's going to diminish the square of the radius. All right, so that's it. Inside, it just increases the electric. So inside the electric field is going to be directly proportional to the radial distance. Okay, guys, that's it.